Network Plus, Common Networking Protocols and Ports. You know, I'm old enough that when I was a kid, the communications that we dealt with were things like walkie-talkies, and we had CB radios, and we had some friends who were ham radio operators. We didn't have all the fancy gadgets that we have today. And we learned early on that there were actually protocols for communicating over these type of networks. For example, as a kid, when you had a walkie-talkie, you knew that when you pushed down the button and you started talking, when you were finished talking, you would say over and then let go, and the other person would know it was time for them to talk. Or if you were done talking completely, you would say over and out and then let go. Same thing with CB radios and ham radios. There's these protocols that are used to communicate between the two endpoints. Well, in this particular nugget here, we're going to look at a lot of common applications and protocols that are part of the TCP/IP protocol suite. And we're also going to identify the ports that they use, which are just like two gates that airlines would use, for example, leaving from one gate and flying across the country and arriving at another gate. We're going to look at the ports that are assigned to these applications and protocols. In this nugget, we have a number of objectives. First of all, we're going to explore that 4-layer TCP/IP suite. We'll look later at the 7-layer OSI model. Then, we're going to look at some common networking protocols, and I grouped these up kind of logically. The 3 really important protocols of TCP/IP would be the ARP, DNS, and DHCP protocols. We'll look at those. Then we'll look at file transfer protocols like FTP and TFTP. Then, web protocols like HTTP and the secure version HTTPS. And then related to HTTPS is SSL/TLS. Then we'll look at mail protocols, mail transfer, POP3, SMTP, and IMAP4. Then over here we've got our management protocols that are commonly used in networking, Telnet and SSH, the network time protocol for time synchronization, the simple network management protocol, SNMP, ICMP, and IGMP for multicasting. Sound good? Alright, let's take a look at the TCP/IP 4-layer suite. You know, it comes as no surprise that this TCP/IP application protocol suite was developed by engineers and scientists and research programmers, people that were part of the defense and military and government research body of the United States and other countries. And so it's no surprise that they had a kind of modular, layered approach to this that would give them some way to define different activities or different actions and functions and tasks at different layers. So we're going to look at this 4-layer model, which by the way is the earliest model of TCP/IP. Maybe you've heard of the 7-layer OSI model. Well, that came later. So we're going to talk about that later in this particular nugget series. But what we're going to look at here are a lot of protocols and services that function at this application layer here, the top layer. This is stuff that programs and services that run on top of the network infrastructure. And we'll look at a lot of these protocols. Actually, we'll look at all of these protocols in this nugget, and we'll look at RIP in a later nugget, okay? And then operating on top of this is the transport layer. And we're going to spend quite a bit of time here in this nugget talking about these 2 main protocols, the connection-oriented reliable TCP protocol and the unreliable connectionless UDP. Now, unreliable doesn't mean that it's not good, it just defines the way that UDP works. TCP stands for Transmission Control Protocol, and UDP stands for User Datagram Protocol. This is typically referred to as the transport layer or OSI layer 4, which we'll look at later. Then you have the internet layer, or what we call layer 3 of the OSI model, and we'll look at some of the protocols that operate down here on layer 3. The Internet Protocol, IP, we'll look at ARP, and we'll also talk about IGMP and ICMP. Then down here you got the link layer, also referred to as the data link layer. This is where your network interface cards work, your NIC card, your wireless radio in your laptop, or your wireless network card. This is where this operates as well. Protocols like point-to-point protocol function down here as well. And then on the bottom we have the physical layer, and this is things like Ethernet, token ring, or other ring protocols like FDDI, frame relay, and ATM for wide area network connectivity. If you're not familiar with these concepts, don't worry. We're going to define them very well in this Nugget series. Now, one of the things that happens is this. As data comes down from the application layer, maybe it's an email message, maybe it's a DNS query, okay? Maybe it's a web page from HTTP, maybe it's a file that you're sending through file transfer protocol, maybe it's a management message or a routing update. Regardless, whatever this data that comes down from the upper application layer and it comes to the transport layer, what happens is this. The transport layer is going to take this message and it's going to add some of its own information to it, its own control information. And this is in the form of a header, okay? And a header is very similar to this. Here's a sample of one of those FedEx labels that you'll take and you'll append to the outside of a FedEx envelope. Imagine if the data is inside one of those FedEx envelopes, whatever it is, and then we want to be able to move that FedEx package and route it across the Federal Express network from one point to the other, in this case from Wisconsin to Lagos, Nigeria. Well, on that particular label, you have a bunch of information on there. You have addressing information, you have priority information, for example, you have other types of data descriptors and issues like that. So this information on the outside of the FedEx package is very similar to the kind of information that TCP and UDP has to add to the package. Think of it that way. And when that particular package arrives at the target, they'll get that package, they'll strip off the label, open up the package, and pull the data out of it. Okay? Of course, all along the way, that information is being read by different participants in this networking process. So if you think about this, all this information that's here on this FedEx label, you could take this information and you could put it into a database, couldn't you? You could have a bunch of records, a record for source address right here. You could have a record for destination address, which is right here. You could have a record for whether it's a priority, what is the priority of the message. You could have some type of tracking information. Okay, it could be a sequence number, for example. You could have other descriptors, and these could all be in this database. And if you took this database of information and you made it, let's say, into just a string of zeros and ones, where the zeros and ones represented this data in this record, and you broke up those zeros and ones into different fields, that's what the header of the TCP and UDP would look like. It's just a bunch of zeros and ones that are appended to the data or to the message. And then you have bits in here that describe where these fields begin and end. And all these zeros and ones represent is all of this information. Addressing information, priority information, tracking information, descriptors. Okay? Now TCP and UDP, they have their own header. And other protocols like IP and IGMP and ICMP, well, they have their own header information as well. So as the data comes down, let's say it's a DNS query, as it comes down to the transport layer puts its header on there, which again, like a FedEx label, and this becomes the data now. This gets passed down to the internet layer, and of course it's going to put, let's say, its IP header on there, which is about, let's say, 20 bytes. We'll say the TCP header is 20 bytes. IP header is 20 bytes. That gets appended to that message. That gets passed down to the link. Okay? And then ultimately, whatever encapsulation you're using down here to send it over the wire or the wireless, okay, that's my wireless, whatever you're going to use here, Ethernet or token ring or frame relay, well, you know what? They're going to add their own header information as well, and they're going to place this out on the physical media. And the physical media could be, again, wired or wireless. And then it uses its own kind of encoding and decoding and algorithms to translate that data into the format that's being used over that physical infrastructure. Now, what we're going to do here, first of all, is we're going to talk about two very important protocols, TCP protocol and UDP protocol, because these are kind of the heart and soul of communications over the global internet. So we'll break down TCP and UDP first here. Now the first thing I want to show you is this. There's an organization called the IETF out there. They're responsible for all of these different standards that are used for these protocols and applications. And so it's imperative that you understand that behind all of these protocols and applications, is a working group of individuals, men and women, who are constantly upgrading the standards, improving and extending the standards, and coming up with new standards. And what's behind all of this is what's called RFCs, request for comments. So if I go in here and type in, let's say, 1918 RFC 18, and by the way, I'm at ietf.org RFC. This is a good place to create as a favorite, because all of these things I'm going to show you, and if you're going to be into networking, eventually you're going to want to read some of these RFCs. This is the basic fundamental documentation. And you can see here is a part of the network working group. Here's all the individuals that are part of this. Okay, and this is the address allocation for private networks, and we'll talk about this later, but this RFC talks about the IP addressing scheme that's used for internal private networks that aren't routed on the public network. Networks like 192.168.0.0, for example. So there's an RFC for that particular topic, and all these protocols we're going to talk about have an RFC behind them as well. For example, here's a great RFC that should be part of your toolkit. It's RFC 1180, and it's a TCP/IP tutorial. This is a nice overview of this TCP/IP suite we're going to talk about here. It introduces it, talks about Ethernet and ARP and IP and UDP and TCP and other network applications. This might be a pretty good bare bones look at TCP/IP. As a matter of fact, you might want to kind of read through this before you take your Network Plus exam. You know, most network communications aren't like sending a postcard to somebody, or, I don't know, putting a note on a rubber band around a rock and throwing it over the neighbor's fence. Most of these are two-way communications that are made up of sessions. They're transactions between two endpoints where information is exchanged back and forth. And there's two primary transport layer protocols that do this for us: TCP and UDP. TCP is a connection-oriented protocol. And one thing that makes it connection-oriented is a three-way handshake is going to take place between these two endpoints. There's also a lot of extra control information that's going to be stored on intermediate devices between these two endpoints to help manage this particular transmission. Now, why is TCP so important for us? Now, the operation of TCP pretty much is self-managing. It does this three-way handshake on its own. It has acknowledgments. It has sequence numbers. It can adjust the size of packets that are sent and received. So it has some of these built-in characteristics. But why TCP is so important to us as network technicians is that a lot of the devices between these two endpoints, like routers, for example, or maybe firewalls, or servers that do what are called proxy services. A lot of these devices between these two endpoints, let's say this host A here at address 192.168.0.1, or Wisconsin, and host B over here at 172.16.0.1 at, let's say, Lagos, Nigeria. There's a lot of intermediate devices between these two endpoints. Some of these reside at the actual premises of these devices, like routers and firewalls and proxies, and other devices are ones that are routed across some type of telco or internet backbone. And this information that's put in the TCP header on this data has a lot of control information in there. And those fields of information are going to handle things like the sequencing of the data packets. So if data packets are sent from host A to host B, they may not arrive in the same order that they were sent. So we want to have them sequenced back into the correct order. We might want to have mechanisms for acknowledging that data was sent and received. We might want to have information stored in memory on routers or on firewall devices that manages the state of this communication between A and B. Whether the connection's open, whether it's closed, do we have to retransmit, do we have to do data flow and congestion detection and congestion avoidance? And this is important because this TCP information can be used to manage security, it can be used to manage congestion or optimization and performance. It can be used to filter out certain types of traffic. A lot of applications and services use TCP, and I may want to filter out certain TCP traffic based on the port numbers they use or the protocols that they use. So when host A sends its first Internet Protocol or IP packet to host B, it's going to embed some of that TCP information in the form of a header into that packet. And one of those fields has zeros and ones in it, and we're going to turn on one of those fields and say this is actually a synchronization packet. I want to set up a synchronization, a connection between host A and host B. Host B is going to answer back in this handshake process with a synchronization and acknowledgement. And then finally, host A will answer back and say, you know what, I'm going to acknowledge that synchronization and that acknowledgement. And once that's set up, now we've got a connection. We can start sending our messages or our data across this internetwork. And we've got devices, intermediate devices, that can manage that traffic for us. For example, like a router or a firewall. Now, I mentioned the TCP header. What's some of the information that's stored in that header? Or think of it as that FedEx label. Well, we've got the source address, the source IP address of host A right here, the destination IP address of source B right here. We might have the source ports that we're using. Okay, I'll put SP and DP. The source port might be, let's say, a number I just grabbed, let's say 1026. Destination port is the service I want to use on this host here. Maybe I want to use a telnet session on this server. Well, I would use destination port number 23. And then I'll have a sequence number. Okay, an initial sequence number, let's say 49092, and this sequence number is going to be used for a wide variety of purposes by both endpoints. And I mentioned this synchronization bit and the acknowledgement bit. There's also a finish bit. Okay, these are just what are called flags. They're just little zeros and ones turned on in this TCP header. And many of the applications and protocols that we're going to talk about throughout this nugget are going to use this connection-oriented, reliable TCP protocol. Now others, however, don't need this reliability and this connection. Maybe they're going to handle the connection themselves in the application. In that case, they might use UDP, User Datagram Protocol. Now UDP is known as an unreliable protocol. Now it just simply means that there's no connection session set up between host A here in Wisconsin and host B here in Nigeria, in Lagos. But it's efficient, okay? It has no delivery guarantees. There's no setup of the connection. There's no three-way handshake that goes on between A and B. There's no termination of the UDP session. There's no congestion management or congestion avoidance. There's no windowing feature that says, okay, we'll allow more packets or less packets. And there's no real ability for these intermediate devices like routers and firewalls to actually store any stateful information about this connection between A and D, because there is no connection. There is no service agreement. So UDP is typically used in simple kind of request reply services or ping pong services. For example, like DNS queries. You know, a DNS query might be sent from A to this server on the internet here to resolve a domain name system name to an IP address. And so it kind of ping pongs between the two. There's no session set up. UDP is also used for what we call flow services. And with flow services, what happens is, this is more in the application layer up there. And the application or the protocol or service itself has the reliability built into it, okay? The delivery mechanisms and other reliability mechanisms are actually written into the application. This would be things like streaming audio or streaming video, voice over IP, the network file system, NFS. These all have functionality built into them. So UDP is thinner, it's lighter. We can use UDP for the transport layer 4 instead of the more cumbersome and stateful TCP protocol. Now these differences will make more sense to us as we start to look at the other applications and services that are used in the TCP IP suite. And we're going to talk about those right now as we look at ARP. ARP stands for Address Resolution Protocol. This is what we consider a maintenance protocol on our local area network. And realize that ARP is a protocol, but it's also an application. In other words, on my system here, this Windows Vista system, I've actually got a program called ARP, and I'll show you here in a second, and it's got little commands I can issue, parameters, and I can see information stored in what's called an ARP cache, which is an area of memory that this protocol uses to store, well, what it does. And what ARP does is it translates IP addresses to MAC addresses. There's a couple of key addresses that are used here, and just like the FedEx package, we've got addresses there as well. So these hosts, here's a laptop, here's a this is my laptop here. This is a workstation. This is a network printer. These are all three connected to a switch, a departmental switch, maybe a Cisco 2960 switch. This switch connects to a router, a layer 3 or a multi-layer switch device, which eventually goes out here to the internet. This is our little network here. And what ARP does is we're looking at two different types of addresses here. We have an IP address assigned, let's say, and we're going to look deeper at addresses later on in this very, very long nugget series here. So a lot of these concepts are going to be reinforced over and over and over throughout these 30 nuggets. So we have 192.168.0.1 is the IP address that's been on this laptop. Maybe it's been assigned by a DHCP service or server. Maybe we manually assigned it. Along with that, the cable here that connects into this switch, the cable that goes to the switch, there's a port on this laptop, and that network interface port also has what's called a media access control, a MAC address, okay, a hexadecimal address. So what has to happen is these devices all have one or many network interface ports with MAC addresses on them. For example, the switch may have dozens of MAC address ports on them. And so what ARP has to do, it has to resolve this layer 2 MAC address to this layer 3 logical network address. The MAC address is not going to change, okay? It's burned in. But this logical address can change over and over and over again as this laptop moves from the local area network out here maybe to a hotel that connects to the internet, or a small office, home office over here, okay? With my little small office, home office, this logical address may change. Well, what ARP does is it resolves this logical address to the physical address. And so what ARP's going to try to find out, first of all, let's say if this particular device wants to connect to a device, let's say out here at 172.30.2.1. This device is first going to say, you know what, I don't know, I have this IP address of this particular host, but I don't have its MAC address to send this particular frame to. So first of all, it's going to decide, is this destination IP address here, is this on my network? Okay, so it will broadcast to say, are you this address? Are you this address? Are you my daddy? Are you my daddy? That kind of thing on this particular device. If not, it's going to then go over here to its default gateway. Okay, and the default gateway here is a router. And it says, you know what, this particular IP address is not on my local network here. So I'm going to go to the default gateway out of my local area network and say maybe it's on some other network. Okay, so that's what ARP does. It's an address resolution protocol. And as it learns these MAC addresses of these hosts on its own network, it will store that information, including the MAC address of this default gateway's interface here. It will store that in a cache in memory, and that's where the ARP program comes in. Let's go down on this Vista machine here and go to Programs, Accessories, and we'll bring up the command prompt here. And we can see that I can type in ARP, and ARP-A says, show me all of the information in the ARP applications cache in memory. So we can see here, as I do an ARP-A, it's showing me now in memory I have a couple of mappings, a couple of IP address to physical address mappings. One of these is static and one of these is dynamically learned. And you can see that 10.0.0.2 is mapped to this physical MAC address here. Okay, it's hexadecimal. and then 224.0.0.22 is mapped to this 01 MAC address. And so as this particular device communicates across the network, its local area network, it's going to store these mappings in its own cache, and it should also have a mapping to its default gateway, or the router that gets it out of this local area network beyond, so that that packet, that frame, can be ultimately routed to its destination point. So ARP is a very important protocol and application that's part of our TCP/IP suite of applications. Now, machines like to use binary, zeros and ones, and machine code, and we know that network interfaces like to use those hexadecimal MAC addresses, and we use the logical IP address, which is the 32-bit dotted decimal. But you know what? Human beings like to use names. They like friendly names. They like their systems and their services and applications to be identified using some type of naming convention. And that's where the domain naming service came in. Now, early on, in the early days of the TCP/IP protocol, there was a handful of universities and research facilities that were a part of this internet, and they used what was called a hosts file. And this was simply just a text file that would map the IP address, let's say 192.168.0.1, to a friendly name. Let's say an FTP server on, we'll say a university called Berkeley, okay? Berkeley.edu. So you'd have a friendly name that would represent this system or this service, in this case the file transfer protocol service or server, at this logical IP address. And this host file would be kind of compiled and passed around from site to site early on. But as the internet grew and as more Unix machines came on board and more microcomputers, this host file became unmanageable. Now, the hosts file still exists. I've got one right here on my Vista machine. I'll show you here in a second. But we needed a new service, and at Berkeley they came up with the Berkeley Domain Naming Service, DNS, which is a hierarchical distributed database for the internet namespace. It's hierarchical in the sense at the top of the hierarchy you have the top level dot, and then underneath that you have top level domains, or what we call, I'll just write over here, TLDs. These are the ones you're familiar with: com and gov and edu, and there's many, many more. There's, .tv, .info, .net. Countries have their own, .ca for Canada, for example. And then below these top-level domains, we have organizations, commercial organizations, government organizations, educational organizations, and the like. You've even got the .org, typically non-profit organizations. And you have, let's say, under com, you might have, let's say, Nugget Lab. And of course, I could have subdomains under Nugget Lab, and so this is just a hierarchy. And you have a system of queries, different types of queries, to resolve these IP addresses to domain names. So, for example, if I go to my web browser and I type in here, let's say, www.nuggetlab.com, and of course, after the .com, there is actually a dot there. There's a top-level domain, so it's the root is dot, and then com is the TLD, and then the domain name, this could be organizational name, company name, whatever, the registered domain name Nugget Lab, and then under that is the web server I'm looking for. I'm looking for a service, the www service, which is typically HTTP on port 80 at the domain nuggetlab.com. If I type that in there, there's an underlying IP address, and so a DNS lookup had to take place to resolve this friendly name nuggetlab.com to the IP address of this web server at the domain Nugget Lab in the TLD com. And so the DNS is a domain naming service, but it's also an application. It's part of the TCP/IP stack. So when you install the TCP/IP protocol stack on your system, for example, Microsoft has their own kind of version of TCP/IP. When I install that, I also get a program called DNS. It's a DNS client which is actually going to do queries. It can also be a DNS server as well. Most Windows systems, especially the server systems like Server 2003 and 2008, also have a DNS server. And this DNS application will use port 53. Okay, TCP and UDP port 53. It uses both. It uses TCP for connection-oriented services to transfer, for example, the database, to make copies of the distributed database and copy it from one server to another. It will use UDP port 53 for the queries, okay, kind of a ping-pong activity for DNS queries. Recursive queries and iterative queries. Now, how do I know that DNS uses port 53? Well, I can find this information out in the same place that I can actually find this original host file on this Microsoft system. Let me show you. I'm going to go to my computer here. I'm going to go to the C drive, and I'm looking for the Windows directory. In the Windows directory, I'm looking for a folder called System32, and then Drivers, and then there's an etc etc folder. Here's the host file, the original host file run it in Notepad, and this is typical of what the host file looked like. Now, back in the early days and on some systems, in some Unix system organizations, this host file may be propagated a lot heavier than this. This is just a couple of examples, but this shows you what this original host file did. It had an IP address mapped to a friendly name. For example, rhino.acme.com. This is just a comment right here, and that little pound sign kind of comments this out as the system parses this file. So at this point, all it would really see is this local host at 127.0.0.1. Also, I can see, for example, here, this IP address mapped to this domain name. Just a couple of examples here. So this is what the original host file does, and it can still be used in your system now. You can configure your client systems and your server systems to actually resolve names by looking at the host file first before doing a DNS query. Or you can say do a DNS query first, and if that doesn't resolve, hey, go look at the host file here in this system folder. Okay, in this case, in the System32 drivers, etc. And it depends on the system where this is located. Now, another important file here is the services. And I'll go ahead and open this up in Notepad, and you can check this out. This relates to the port numbers, the TCP and UDP port numbers that are used. Different services use different port numbers. So, for example, if a client's trying to reach a DNS server, if you look down here, we can see DNS domain. It's going to use 53 TCP and 53 UDP. So if it's trying to initiate a file transfer to a DNS server, it may grab a ethereal port somewhere way up there high, but the destination port will be the IP address plus port 53. And so you'll need to know this for your Network Plus exam. Some of the most common services and the port numbers. For example, FTP, which we'll talk about, uses two different ones. It uses 21 TCP for its control data. For that three-way handshake that takes place that I talked about, it'll use port 21, and then once the session is set up, it'll send data on port 20. Secure Shell, which is kind of a secure version of Telnet down here, uses port 22. Telnet uses port 23. SMTP Mail uses port 25. For example, let's see, Domain. We already looked at that one. BootP, which is DHCP, uses UDP 67 and 68. So again, you won't need to know all of these. Like you won't need to know Gopher and Finger, but you will need to know HTTP. It uses TCP port 80 and others as we go through this particular course. So this services file is on your system, and it would be a good idea for you to know about it. And this gets updated. As you can see here, as I scroll down here, this is a pretty new operating system. So look at all the different services that have been added, and the organization, the IANA is the one that's responsible for registering these domain names and these service numbers. Okay, so you can see as we get down here into newer services like video and audio streaming services and instant messaging services, you can see some of the newer services, they actually register these port numbers, okay, TCP and UDP port numbers for different types of services. You see Microsoft registers a lot of those. The CIFS, which is the file system used by Windows, uses TCP and UDP. And so as time goes on, and again, this is a 16-bit number, so there's 65,536 of these possibilities, but some of these are registered and used by services and applications. So This is the services file, and it's located on your Windows system in the etc. subdirectory of drivers System32 Windows. Let's talk about DHCP now. Next, let's talk about DHCP, the Dynamic Host Configuration Protocol, which is based on the old bootp service. And you can see here, if I go to the configuration, the properties for my network connection, you can see I can go down here and choose IP protocol version 4, not version 6, but version 4. Double click on that and you can see my properties here where I can configure my IP address, my subnet mask, and the default gateway. The default gateway goes back to that discussion with ARP, where if I was looking for a computer and I couldn't find it on my local area network, I'm going to go ahead and send it to my default gateway or a router, because I'm assuming that this host that I'm trying to reach is beyond this router as my default gateway. Now I can say I can go ahead and manually configure all this information in here, or I can rely on a system from Microsoft called APIPA, which is a PIPA, which would go ahead and fill this in for me if I couldn't manually configure it or if I couldn't get it automatically. But we're not going to use either one of those methods. We're not going to use the manual method or the PIPA method from Microsoft. We're going to obtain an IP address automatically from a DHCP server. So the first time I bring this up, and by the way, I'm also asking to get my DNS server as well, okay? And DNS goes back to my previous discussion, which is the server that's going to resolve my queries to map my IP addresses to friendly domain names. So what's going to happen is this client's going to come up initially. It's going to go through a process called DORA. It's going to do a discovery. It's going to make a broadcast of UDP packets, and it's going to use that UDP port number that I showed you earlier in that services file to a server out there. So it's going to broadcast on this network or subnetwork looking for a DHCP server or a relay server. And when it finds one, a DHCP server will make an offer to my client. So D is for discovery, O is for offer. Once I get the offer, I will respond to the offer with a request to the server. The server will respond to the request by saying, you know what, I acknowledge that, and here is now your IP address and your subnet mask and your gateway and your DNS server. Now I can see this information. For example, if I go to Programs, Accessories, Command Prompt, and I use the program ipconfig /all, ipconfig, and then the parameter of all, I can see what I'm getting from this DHCP server, because I can see here, if I find the right area, IP configuration, okay, I am getting it through DHCP. DHCP is enabled. Right here it says yes, and you can see I'm getting a address, an IP address. You can see my IP address right here. IP address version 4 is 10.0.0.4. And also DHCP is giving me my default gateway of .2, my DHCP server at .2. I can also see my DNS server is also at address .2. So my DNS server, my DHCP server, and my default gateway router are all the same box. As a matter of fact, it's a wireless router that's going to my DSL connection to my IP provider. And so we can see that it's DHCP that is giving us this configuration here in the ipconfig /all command. And if I wanted to, I could go ahead and change this and manually configure it. I could manually populate my DNS server, but DHCP is a service that allows us to automatically assign an IP address, a subnet mask, a default gateway. We can assign a bunch of stuff. Let me go ahead and show you on the server side here. Here's a Windows 2008 server that you can configure as a DNS server. And what you simply do is you go and you start the DHCP service process on there and you create a scope. A scope is simply a range of IP addresses. So what we've done here on this 2008 server is we've created a scope of 192.168.1.50 through 100, okay? 50 addresses. Give it a subnet mask, a 24-bit subnet mask, and then we also assign the default gateway to this scope, okay? Now we can assign even more information than that to this scope. And again, this scope is going to have a lease. So whenever you lease out that information to a client, and on the previous slide, if I wanted to go back and look at the ipconfig results, that particular address and subnet mask information was also leased out to this client as well. But you can see here now under the DHCP service on this 2008 machine, I've got my scopes, which shows my address pool, but I can also go and reserve addresses for certain things like servers and printers so that those are not automatically handed out to laptops, for example. I can also configure scopes, and you can see here some of the scopes. Some of the scopes are what is your default gateway? Scope number 3. What's your DNS server? Scope number 6. What's your DNS domain name? Scope number 15. And there's actually 255 values here. It's an 8-bit number. So over 250 different types of things can be configured manually and leased out to these clients besides just the IP address and domain name. As a matter of fact, I'm up on the internet here and you can see here's a list of all the different things and the RFCs that are related to them, all the different things that can be assigned and leased out to these clients with their DHCP lease well beyond just the IP address and subnet mask. All this information can be leased out depending upon your organization, your network infrastructure, your environment, the product, the platform you're on, and you can see all the way up to 255 is where it ends because it's an 8-bit value. In other words, in the DHCP header, that field of information there is 8 bits long, 8 zeros and 1s. So this is the options that you can give out with the information. And it shows here BootP DHCP. DHCP is just the new version of the old BootP protocol. Now we're going to be talking about protocol analyzers and packet sniffers later on in this Nugget series, but I just couldn't help myself. I wanted to go get Wireshark off the internet. It used to be called Ethereal. It's a free download. It's a packet sniffer, and you can get it for free, wireshark.com or whatever. Go for it. I downloaded it, and I also got, there's a bunch of these PCAP files, these existing captures, and I've got a DHCP here, and you can see here's the process the DHCP goes through. The DORA, discover, offer, request, and acknowledgement. And you can kind of see here, what's great about this is you can actually download this for free, go get the DHCP capture, and you can see, you know, the OSI model in action. Okay, here's Ethernet down here, here's layer 3, the Internet Protocol. You see we're IP version 4, user datagram protocol. This is what DHCP uses, and lo and behold, there's the ports that are used by DHCP and UDP. UDP port 68, UDP port 67. Here's the actual DHCP application layer protocol itself. It's called the Bootstrap protocol, and you can see here it is. And you can, this is the original discovery packet. It's a broadcast packet. Here's the offer from the DHCP server. The DHCP server is offering address 192.168.0.10. Okay, it's offering it from the BootP or DHCP server at 0.1. You can see other options. I talk about those options that are used. Here they are. You can see it's offering that IP address with this subnet mask. It's offering a lease of 1 hour. And again, this information is leased out, and it's the DHCP server and the scope of the IP addresses on that server that determine what the lease time is. You would probably use a short lease time like 1 hour at maybe a wireless hotspot or a service provider of some kind. Typically in an enterprise organization, you're going to have a lease time of 7 days, maybe up to 10 days. And you can see here's the server ID address. So, you know, we're seeing those options. This is only like 6 or 7 of the options of the over 250 possibilities. But as I mentioned, these are fields in the DHCP or BootP header. And there they are right there. You can see them. And even as you click on these, you can even see the information show up down here in the bottom in the data area. It's pretty cool. That's the offer, the request, and the acknowledgement. Here's the final acknowledgement from the client. Client number 0.10 is going to go ahead and accept it. And you see other values, renewal time values, rebinding times. Depending upon how long the lease is, the longer the lease is, the longer the renewal times and the rebinding times. Okay, and so this is just information that's doled out through the DORA process: discover, offer, request, and acknowledgement. And as a matter of fact, what will happen is if this particular client were to turn off Okay, turn it off for a couple of days, even if the least expired, maybe 2 hours later, and come back on, it's actually going to skip the whole discover process. It'll literally remember what it had last time, and it will go right to the request. It'll simply go to the DHCP server and request the same configuration information it had previously. And if this IP address and lease is available to this client, well, instead of going through the cumbersome 4-step process, it just goes through a 2-step process, and the DHCP server goes ahead and says, you know what, I'm going to acknowledge your request, and I'll just give you the information that you had last time. Okay, so this kind of streamlines the DHCP process. And so we see some of the options, some of the protocols, some of the behavior here kind of come into life. And again, you can use this Wireshark. This is a great tool because you can go up, and I would highly recommend, and we're going to talk about these tools later, but I would highly recommend going up and getting this tool. And then there's all different kinds of captures of all different types of network traffic. That's a great way. If you don't have, you don't have the ability to go use one of these tools in a live enterprise environment, well, you can still go get these samples of these captures, and you can see this type of traffic and see the behavior of it and see the the 7-layer OSI model here in action. So that's the DHCP protocol and its 4-step DORA process: discover, offer, request, and acknowledgement. Well, I'm looking at my list here of topics we're going to cover in this nugget, and obviously we're not going to get through to the end. We've only covered basically the first 2 bullet points, but that's okay. We'll make this a part 1, Common Networking Protocols and Ports Part 1. When we get to part 2, we'll review and do an overview of these remaining protocols, okay, FTP, TFTP, HTTP, and so on, these management protocols, as we wrap up. So we're going to wrap up this Common Networking Protocols and Ports Part 1, and I'll see you in the next nugget as we wrap up the rest of these networking protocols. I hope this CBT nugget has been informative for you. I want to thank you for viewing.